Welcome to Geometric Physics. This is a two-quarter sequence, and over the next 20 weeks we are going to build the differential geometry that classical physics is actually written in and then use it. Today is orientation. There will be very little machinery and a lot of pointing at where we are going. The reading for today is the overview in Frankel and the first 7 sections of Marsden and Ratiu. Let me start with the claim this whole course rests on. Classical physics is differential geometry. I do not mean that geometry is a convenient language for describing physics. I mean the objects are the same objects. The configuration of a mechanical system is a point on a manifold. A velocity is a tangent vector. A momentum is a covector, which is a different kind of thing, and we will spend a whole lecture on why. Phase space is the cotangent bundle carrying a two-form called omega. An observable is a function. Time evolution is the flow of a vector field. A symmetry is a Lie group action, and a conservation law is a component of something called a momentum map. That is the first quarter. In the second quarter, the same list continues. The electromagnetic potential becomes a connection on a line bundle, the field strength becomes its curvature, and a Yang-Mills field becomes a connection on the principal bundle. Here is the shape of the two quarters in a single picture, and I want you to keep it in mind even before it makes sense. In the first quarter, we start with a phase space carrying a symmetry group. The symmetry produces a momentum map, which is a function from the phase space to the dual of the Lie algebra. Then we quotient by the symmetry and land on a smaller space called the reduced space. In the second quarter, we start with Yang-Mills theory, whose symmetry group is the group of gauge transformations. The momentum map of that action turns out to be the Gauss law. Quotienting by the gauge group gives the physical phase space. Those two rows are the same theorem. In the first quarter, the group is finite dimensional. In the second quarter, it is the group of gauge transformations, and the momentum map is the Gauss law constraint. Let me make that concrete. Here are 4 systems we return to every week this quarter. The 4 are these. First, the free rigid body, a finite dimensional system whose configuration space is 3-dimensional. Second, the heavy top, which is the same body with gravity switched on, and where the symmetry is broken. Third, the ideal incompressible fluid, which is infinite dimensional, and whose configuration space is the group of volume-preserving diffeomorphisms of the container. Fourth, the Maxwell-Vlasov system, which is as a plasma, meaning electromagnetic fields, coupled to a distribution function. Right now, those 4 look like they have nothing to do with each other. One is a spinning top, and one is a plasma. By week 10, we will write all 4 of them in the same equation. Start with the free rigid body. Take a rigid body with one point held fixed, so it can rotate but not translate. What is a configuration? It is an orientation of the body in space. Concretely, it is the orthogonal map that takes the body frame to the spatial frame, and it preserves orientation. So the configuration space is exactly the rotation group, SO3, which is the set of 3 by 3 matrices A with a transpose A equal to the identity and determinant equal to 1. Notice 2 things. The configuration space is a 3-dimensional manifold, and it is definitely not R3. And it is a group. That the configuration space carries a group structure is not a coincidence to be noticed and then ignored. It is the entire story. Now here is the puzzle I want to leave you with. Write capital Pi for the angular momentum measured in the body frame, and write I1, I2, I3 for the principal moments of inertia. Then the motion is governed by Euler's equations, which say that the time derivative of the vector pi equals pi cross omega, where omega is the angular velocity in the body. Count dimensions. The configuration space SO3 is 3-dimensional, so the momentum phase space T star of SO3 is 6-dimensional. But Euler's equations are 3 equations in the 3 components of pi, and they close. Nothing else appears in them. So where did the other 3 dimensions go? Hold that question. It is not special to the rigid body, and the answer, which is called Lie-Poisson reduction, is the punchline of lecture 20. Second system, take the same rigid body, but now let gravity act, and let the fixed point not be the center of mass. This is the heavy top. The energy is the rotational kinetic energy plus a gravitational term, which depends on capital gamma, the direction of gravity as seen in the body. Now SO3 is no longer a symmetry. Gravity picks out a vertical direction, so only rotations about the vertical survive, and that is a circle group. But the equations still close, now on 6 variables instead of 3. The time derivative of pi picks up a torque term, and gamma satisfies its own equation. The time derivative of gamma equals gamma cross omega. Breaking SO3 down to a circle does not destroy the structure. It replaces the group by a semidirect product, SE3, which is SO3 acting on R3. We will see this properly in week 10. Third system, and now we jump to infinite dimensions. Take a container, a region in 3 space filled with an ideal incompressible fluid. What is a configuration of a fluid? It is a record of where every particle has gone. So a configuration is a map from the container to itself, smooth, invertible, and volume preserving. The configuration space is therefore the group of volume preserving diffeomorphisms of the container. That is an infinite dimensional group. The kinetic energy of the fluid defines a right invariant metric on that group. And here is Arnold's theorem from 1966. The Euler equations of an ideal fluid are the geodesic equations of that metric. Read that again. An ideal fluid is a rigid body whose group is the diffeomorphism group instead of SO3. The Euler equations of the rigid body and the Euler equations of a fluid are literally the same equation on different groups. Fourth system, a collisionless plasma, described by a distribution function on single particle phase space, coupled to the electromagnetic field that the plasma itself generates. The Vlasov equation says the distribution function is transported along the flow generated by the Lorentz force, and Maxwell's equations are sourced by that same distribution function. Morrison, Marsden, and Weinstein discovered that this whole system is Hamiltonian, with respect to a bracket on the distribution function and the 2 fields. That bracket is not the canonical one. It has the same Lie-Poisson shape as the rigid body's bracket for a group that combines diffeomorphisms of phase space with gauge transformations. Now, nobody could guess that bracket by inspection. It was not guessed. It was derived by starting with an ordinary canonical system on a cotangent bundle and quotienting by a symmetry. The strange bracket falls out of the quotient. So here's the pattern laid out. Take the free rigid body. Its configuration space is SO3. Its symmetry group is also SO3. Its reduced variable is pi, living in the dual of little SO3, which is R3. For the heavy top, the symmetry is broken down to a circle, and the reduced variables live in the dual of little SE3. For the ideal fluid, the configuration space and the symmetry group are both the volume-preserving diffeomorphisms, and the reduced variable is the velocity field. And then there is a 5th row, which belongs to the 2nd quarter. For Yang-Mills, the configuration space is a space of connections. The symmetry is the gauge group, and the reduced space is connections modulo gauge. In every row, the configuration space is a group, and the reduced equations live on the dual of its Lie algebra. That is the Euler-Poincare or Lie-Poisson picture, and it is what we are building toward. That was the mechanics. Now let me say why differential forms and not vector calculus are the language we will use. Frankel opens his book with a problem from engineering, and it is the right place to start. Take an elastic cylindrical rod and twist it. Now cut the rod along a surface. The material on one side of the cut pulls on the material on the other side, and the total force across the cut is the integral over that surface of something called the traction. So here is the question. What kind of mathematical object is the stress? It is not a vector field. You cannot evaluate it at a point and get a force out. You have to hand it a surface first, and only then does a force appear. So the stress is a machine that eats an infinitesimal-oriented surface element and returns a vector. That is a vector value 2 form. Cauchy discovered this in 1822, and Cartan gave it its name about a century later. So what is a K-form informally? A K-form at a point is a rule that takes K tangent vectors and returns a number. It is multilinear in all K slots, and it is antisymmetric, meaning that if you swap 2 of the arguments, the sign flips. That antisymmetry is not a technical convenience. It encodes oriented measurement. Write down that alpha of v comma w equals minus alpha of w comma v. What that says is this. Sweep out an area by going along v and then along w. Now sweep it the other way, along w and then along v. The 2 answers differ by a sign. three consequences we will lean on constantly. First, K-forms are exactly the objects you can integrate over K-dimensional surfaces without choosing coordinates. Second, on an n-dimensional manifold, there are no non-zero K-forms for K bigger than n. Third, the change of variables Jacobian is built into them, rather than bolted on afterwards. Let me press on that third point, because it is the one that converts people. Remember how surface integrals work in multivariable calculus. You parametrize the surface, you write down a function, you multiply by the magnitude of the cross product of the two partial derivatives, and then you prove that the answer does not depend on which parametrization you chose. Four things are happening there. The integrand is a function. The Jacobian factor is inserted by hand. Independence of parametrization is a theorem you check. And orientation is handled by convention, with forms all four collapse. The integrand is a 2 form. The pullback is the Jacobian. Independence of parametrization is automatic by the chain rule, and orientation is built into the anti-symmetry. Here is the way to hold this. Think of every square root of g in a physics textbook. Think of every determinant of a coordinate change and every right-hand rule. Each one is a differential form that has been flattened into components. Forms are what those expressions are trying to be. There is a single operator written d that takes k-forms to k+1 forms. It is characterized by three properties. It is linear. It satisfies a signed Leibniz rule across the wedge product. And crucially, d of d is 0. On functions, d is just a differential. And in three-dimensional space, under the usual identifications, the sequence of exterior derivatives from 0 forms up to 3 forms is exactly gradient, then curl, then divergence. So the statement d of d is 0 contains two familiar identities at once. Curl of a gradient is 0, and divergence of a curl is 0. And then there is Stokes' theorem, which says that for a compact-oriented manifold M with boundary, the integral over M of d alpha equals the integral over the boundary of M of alpha. The fundamental theorem of calculus, Green's theorem, the classical Stokes theorem, and the divergence theorem are all the same statement in dimensions 1, 2, 2, and 3. We proved this in Lecture 4. Let me show you where that leads as a preview. Take the electric and magnetic fields and assemble them into a single 2 form on spacetime, called F. Then all four of Maxwell's equations become two statements. F equals 0, and d of the Hodge star of F equals J, where J is the current. Unpack that. dF equals 0 gives you the divergence of B being 0 and Faraday's law. The second equation gives you Gauss's law and the Ampere-Maxwell law. Now apply d to the second equation. Since d of d is 0, you immediately get dj equals 0, and that is charge conservation. So charge conservation is a corollary of a triviality about the exterior derivative rather than an extra-physical law. And because dF is 0, locally f is d of something, call it a. That something is not unique. You can add d of any function to a without changing f. That non-uniqueness is gauge freedom. In the second quarter, we learned that a is a connection and f is its curvature. That is Lecture 29. So much for the geometry. Let me come back to the mechanics and say what structure we are really after. Classical mechanics comes in two pictures, and you have met both. In the Lagrangian picture, you choose a configuration space Q. On it, you write a function L of position and velocity. Then you demand that the integral of L over a path be stationary among paths with fixed endpoints. That gives the Euler-Lagrange equations. This picture is more fundamental in one sense, because it is variational, and because it generalizes directly to relativity and to field theory. In the Hamiltonian picture, you define the momentum as the derivative of L with respect to velocity. You form the energy H, and you get Hamilton's equations. This picture is more fundamental in a different sense, because it is built on energy, because it exposes the symplectic structure, and because it is what quantizes. The Legendre transform relates them, and we will see exactly when it is invertible. The thing to hold on to is that both pictures survive on a manifold with no coordinates at all. That is what makes them geometry rather than bookkeeping. Now, let me show you the single structure that runs the whole quarter. On the cotangent bundle of Q, there is a one form defined with no choices whatsoever. Here it is. Stand at a covector alpha at the point Q. Take a tangent vector v to the cotangent bundle at that point. Push v down to Q using the projection. Then feed the result to the covector you are standing on. That number is theta of v. In coordinates, theta is p sub I dqi, and we define omega to be minus d theta, which in coordinates is dqi wedge dpi. With that in hand, Hamilton's equations become one intrinsic statement. The interior product of xh with omega equals dh, and the Poisson bracket of two functions is omega evaluated on their two Hamiltonian vector fields. No coordinates, no metric, no choice of q. Just the cotangent bundle and the exterior derivative. Every conserved quantity, every canonical transformation, and every reduction theorem this quarter is a statement about omega. Last piece of the preview, Noether's theorem stated loosely. Suppose a Lie group G acts on the configuration space Q, and suppose the Lagrangian is invariant under that action. Then for each element xi of the Lie algebra, there is a conserved function on phase space, obtained by pairing the covector you are standing on with the vector field that xi generates on Q. Package all of those together for every xi at once, and you get a single map from phase space to the dual of the Lie algebra. That map is called the momentum map. Run down the examples. If the group is translations, the momentum map is linear momentum. If it is rotations, it is angular momentum. If it is time translation, it is energy. If it is the circle group acting by phase rotation, it is electric charge. And if the group is the gauge group of a Yang-Mills theory, the momentum map is the Gauss law constraint. We do that one in lecture 40. So let me finally answer the question I left you with earlier. Where did the three dimensions go? The phase space T star of SO3 is six-dimensional. The group SO3 acts on it by left translation, and it acts freely. So we may form the quotient, and that quotient is the dual of little SO3, which is R3. That quotient is exactly pi space. The quotient is not a symplectic manifold. It is odd-dimensional, so it cannot be. But it does carry a Poisson bracket given by minus pi dotted with the cross product of the two gradients. And Euler's equations are exactly the statement that the time derivative of f is the Poisson bracket of f with the energy. That bracket also has a Casimir, a function whose bracket with everything vanishes, namely the squared length of pi. So the motion is confined to spheres. Intersect those spheres with the energy ellipsoid and you recover Poinsott's classical picture of rigid body motion. 3 dimensions of the phase space were absorbed by the symmetry group. What is left is the dual of the Lie algebra with its Lie Poisson bracket. Let me close with the practical matters, which will take about 5 minutes. There are 2 required texts, and they do quite different jobs. Frankel, The Geometry of Physics, 3rd edition, is the primary text for both quarters. It carries all of the geometry. It is computational, its exercises are embedded in the text, and it is written for people who want to calculate. Part 1 is our review, and Part 3 is essentially all of the second quarter. What it does not contain is mechanics with symmetry. The phrase momentum map does not occur anywhere in its 749 pages. Marsden and Ratiu, Introduction to Mechanics and Symmetry, 2nd edition, is the secondary text, and it supplies exactly what Frankel lacks: symplectic and Poisson geometry, momentum maps, and reduction. One practical note: Chapter 4 of Marsden and Ratiu is not assigned. It is a 25-page crash course in manifolds and forms that Frankel Part 1 does properly. Read Frankel chapters 1 through 4 instead. That is the only place the 2 books overlap. Assessment for this quarter. There are 5 problem sets due in weeks 2, 4, 6, 8, and 10, and they are worth 75%. The remaining 25% is a short expository note, 5 to 7 pages, due in finals week. The note asks you to take one worked example from the quarter and explain it to somebody from a different discipline than your own. Collaborate on the problem sets. Write them up alone. If you find the pace of the first 2 weeks fast, there are 2 books on reserve. Chapters 2 and 3 of Holm, Schma, and Stoica are gentler than either required text. Chapters 7 through 9 of Arnold are worth reading for pleasure. 2 more books, Abraham and Marsden's Foundations of Mechanics and Marsden's Lectures on Mechanics are free and legitimate, and links are on the syllabus. A word about who is in this room. There are mathematicians here, and physicists and engineers. Each of you will find one half of this course easy and the other half strange. That is by design, and it is why the final note asks you to explain something across the gap. Let me summarize the 5 things to take away from today. 1. Mechanical configurations live on manifolds. Velocities are tangent vectors, momenta are covectors, and phase space is the cotangent bundle. 2. The cotangent bundle carries a canonical one-form theta and a symplectic form omega equal to minus d theta defined with no choices at all. Hamilton's equations are the interior product of xh with omega equals dh. 3. Differential forms are the objects you integrate. Antisymmetry is orientation. The pullback is the Jacobian, and d of d is 0 contains curl of gradient, divergence of curl, and charge conservation. 4. A symmetry produces a momentum map from phase space to the dual of the Lie algebra, whose components are conserved. Quotienting by the symmetry is called reduction. 5.4. Apparently unrelated systems. The rigid body, the heavy top, the ideal fluid, and the Maxwell-Vlasov plasma are the same reduction on different groups. For Lecture 2, read Frankel Chapter 1, pages 3 through 36, and sections 1.8 through 1.10 of Marsden and Ratiu. We build manifolds carefully. Problem set 1 is posted, and is due at the start of week 2.